Last week we did an example involving cause and effect, and what we showed is that if you can have a situation where something is traveling faster than the speed of light, a material object like a spaceship, or it actually generalizes to any message, any information type message where you can get from one point to another point, that you run into problems with cause and effect. There are contradictions involved. So let's just review what that situation was, and then we're also going to apply our space-time diagrams to the situation and visualize it in another way to get a better idea perhaps of what was going on. So remember the situation we set up was that we had the bad guys and the good guys, and they signed a treaty at the bad guys' planet in year 0, at which point the good guys took off in their ship at 0.6 times the speed of light. And remember, of course, they're traveling along the x-axis. This is their world line on the space-time diagram of the bad guys' frame of reference, the frame of reference of the bad guys' planet. So it's xbg here and tbg for the bad guys. In the intervening years, the 4 years between when the treaty was signed and the good guys took off, the bad guys invented a faster-than-light spaceship. And so in year 4, by which time they perfected it, they set off in their faster-than-light spaceship, which could go a speed 3 times the speed of light, and caught up to the good guys at time t equals 5 years, at which time the good guys had traveled 3 light years away. Remember, they were traveling at 0.6 c. So what that enables them to do within 5 years, 5 times 0.6 c, gives you the 3 light years. Bad guys could travel 3 times the speed of light, and therefore it only took them 1 year between 4 and 5 to get to that point. So they met actually, remember, if you're visualizing this along the x-axis, this is not the actual intersection point on the x-axis where it actually occurred. That would be right here. In other words, the good guys were traveling along the x-axis. This is a space-time diagram showing their progress through time as well. And the bad guys catch up to them and pull off their sneak attack at that point. And we analyzed it from the bad guy frame. The launch occurred at 4 years, and the attack was at 5 years. And then we analyzed it from the good guy's frame of reference using the Lorentz transformation and discovered that the attack occurred at 4 years in their frame of reference, but the launch occurred at 5 years. In other words, the attack occurred even before the super spaceship had been launched, and therefore clearly a violation of cause and effect. You can't have an attack if the spaceship hasn't maybe even been invented yet and certainly hasn't been launched at that point. And therefore the conclusion is that faster-than-light travel is impossible because we've never seen in all our observations a violation of cause and effect. Now that doesn't mean perhaps in some case in the future we may discover something like this. There's a violation, but everything we know, all the experiments we do, says there's no violation like this of cause and effect. Again, some of you may be thinking of things like in quantum physics, which get a little strange, but even in quantum physics, the special theory of relativity has been shown to hold in situations like this, where you can't travel faster than light. So here's a redrawn diagram. Same diagram, except what we've done here is drawn our combined diagram. So again, we have the axes for the bad guy's frame of reference, and then we've put in the good guy axes, the x-axis and the time axis for the good guys. And we've also drawn in the lines of simultaneity. And I've tried as much as possible to make this to scale. Didn't quite get it all right there. But the key thing here is that, of course, you got your 2 axes as we've shown here. The speed of light in these units with, again, it's years, light years and years. Speed of light would be a 45-degree line there. And so what do we see from this? Well, remember the lines of simultaneity in any frame of reference are going to be parallel to the x-axis. The x-axis defines everything that occurs at a certain time, or any given horizontal line on the bad guy diagram, any given horizontal line defines a line of simultaneity. Everything that's going on, say at t equals 4, is on this line. When we have the skewed axes, everything that's going on at a given time is a line parallel to the x-axis. And so I've drawn in a number of these lines here, so they're just all parallel to the x-axis. And if we analyze this, okay, so just to be clear here, it means the x-axis is when the xgg axis is all events when tgg equals 0. In the good guy's frame, that happens at t equals 0. And note, that's when they set off from the planet. We define that as our origin point. So that's at 0. Then here is a little while later, this line, and then a little while after that is this line, and so on and so forth. And that tracks their measurement of time as they move along. So what happens here then? Well, we get up to where the sneak attack occurs, and note that that's, if we're just counting lines here, it's not quite accurate. We've got 1, 2, 3, 4, about 4.5 lines of simultaneity. Technically, if I draw the lines exactly as they should be, we'd be getting the answer 4 here. It'd be at 4 years, but these lines are not drawn exactly to 1 year per line. A little bit less than 1 year per line there. But clearly it's 1, 2, 3, 4, and a little bit more is where the sneak attack occurs. But look where the launch occurs. It's 1, 2, 3, 4, 5, and almost 6 there. So clearly from the diagram, without even doing any calculations, as long as we get our axes drawn correctly, we can see that in the good guy's frame of reference, the launch occurs after the attack. And in fact, in a sense, the good guys would see the attack occurring here, assuming they're still around. Somebody observing, maybe if the good guys had 2 ships and one ship got attacked, the other ship would see actually the bad guy's ship instead of go from the launch point here to the attack position, it would go from the attack point, position there, and travel backwards to the launch point, and then presumably see it get disassembled and all that. So it almost, in a sense, would be like time running backwards for the good guy's frame of reference. And of course, again, we just don't see things like that happening in real life. Time flows in one direction. And so we can't have a situation where time flows in the positive direction in one frame of reference and the negative direction in another frame of reference and make it consistent with physical reality as we know it. Okay, so that's a nice example of how we can use space-time diagrams when we get both things on here to see what's going on with the situation. Now, one other point here I want to make, I'm going to try to draw in the 45-degree line here for a world line of a light beam, say. So, I'm just going to eyeball this, but actually we can do a little bit better. We'll do 4 here, and that's about right there, roughly speaking. I might be off a little bit there, but something like this. So, okay, so there is blue light there. So this is the world line of a light beam traveling along. It should bisect these 2 axes. I got it off slightly, but it bisects the 2 axes here, bisects any of the axes we draw. And from this we can note that if you have a line whose slope is less than the speed of light, world line, in which we've talked about before, that means this is a velocity greater than the speed of light, and that's where you can get this crossing of lines of simultaneity. Note that at the speed of light, it does not cross lines of simultaneity in the backwards direction like this one does. As soon as you get something bending down so that it's greater than the speed of light, then you can get this crossing of the lines of simultaneity in a reverse direction, in a backwards direction. And this is just a graphical way of saying this thing we've said several times now, is that you can't go faster than the speed of light. And so that is an example then of this cause and effect relationship that we need to keep consistent. And we'll actually, this week, as we look at several different paradoxes, we'll come back to, at certain cases, using our space-time diagrams to visualize what's going on, as well as do the Lorentz transformation analysis that we've done before.